May, a powerful earthquake was recorded off the North Pacific coast of Russia, resulting in a tsunami that triggered alerts across the Pacific Ocean basin, including coastal communities in Alaska, California, and Hawaii. For hours, buoys throughout several networks, including the Deep Ocean Assessment and Reporting of Tsunamis Network, or DART, tracked the tsunami's speed and resulting wave heights, giving emergency officials throughout the region critical data points to decide if and when to issue evacuation alerts. As the waves made their way across the ocean, traveling as much as 500 miles per hour, engineers and scientists were running models, collecting data, and watching. Thankfully, as the tsunami dissipated greatly, causing minimal damage to the Hawaiian coastline. For decades, the U.S. Army Engineer Research and Development Center, in collaboration with the federal agencies and universities, has used buoy data to develop, enhance, and share high-performance wave and storm modeling, which were tested and will be further enhanced with data collected from this recent event. I am Shelley Tingle with ERDC's Corporate Communication Office, and joining me for a conversation about this tsunami and ERDC's research in this area are Drs. Kate Brodie and Ali Abdolali, oceanographers with ERDC's Coastal and Hydraulics Laboratory. Thank you, Ali and Kate, for joining us today. Ali, I'm going to start with you. As oceanographers, what did you find most interesting as you watched the tsunami make its way across the Pacific?
Well, tsunamis are very famous for their great speed and their great amplitude when they get closer to the coastline. So as you might know, tsunamis travel at high speed, like a jet, 200 meters per second in the deep sea. Also, they are very tiny in deep sea, so they are not noticeable. But when they get closer to the coastline, they become larger and larger because of their properties. So, and they become devastating. So in the Pacific Basin, we have had a lot of historical tsunamigenic events, but not all the earthquake generates tsunamis. So tsunamis can be triggered by also other mechanisms like volcanic eruption, landslide, earthquakes, but some of the earthquakes also are not tsunamigenic. So the distinction between a tsunamigenic or a non-tsunamigenic event is if they generate such waves. And then as they propagate very fast, we need to warn people and prepare for evacuation, something like that. So if the earthquake is very close to the coastal communities, to do the prediction, we need to react very fast, right? So we need to have some system in place that do the modeling or read the observations and then provide some analysis on the fly for the port authorities, for the coastal communities to issue warnings. But as they get further away and they go and propagate in the Pacific Basin to get to, for example, for this scenario, it happened in Russia, but then it propagated across the Pacific Basin and it reached all the coastal communities in California, in Oregon. So these are some very interesting phenomena that we can see. So I mentioned about the detection of the tsunamis, and I know the conventional ways, they go and detect the tsunamis by DART observations. That's a program that I think NOAA put in the ocean in late 90s. And then after the catastrophic 2004 Sumatra, which killed almost 200,000 people, then that program became more serious and also widely known internationally. And then since then, we have been studying the observations of the tsunamis by these DART buoy. And we are using those observations to quantify our models in terms of performance, accuracy, etc. So if we are talking about long distance tsunamis, that's one way to predict tsunamis by measuring the tsunami itself by the DART observations. But what about if the earthquake is very close to the coastal community? If the earthquake happens on the other side of the Pacific, near the US lands, then there is no time for the waves to get to the DART observations, and we issue the warnings. We have been lucky that we haven't seen much of these events recently, but if one of these faults get activated in the other side of the Pacific, then that's a devastating event.
From my perspective, I was scientifically really intrigued by the effects that the tsunami might have on our coasts and how it could potentially, if it had been a lot larger and a lot more devastating, really changed the shape of our coast and where the sand was in our systems and the impacts that would have on the different communities. And, I think as Ali's talked a lot about is the advantages of having accurate early warnings of the potential tsunami. I think, Hawaii, for example, was pretty fortunate. They had a lot of time to watch the wave come across the Pacific because of the location of the earthquake, but we won't always have all that time.
Ali, during the reporting, we heard a lot about readings from buoys at different points in the Pacific. What role does this network of buoys around the world play in studying and understanding oceans and particularly waves?
So first, I think that the main purpose of having these buoys are for at least for tsunamis, for tsunami warning. So we need this data to once the tsunami arrives to a DART observations or any other types of observations to issue warning, right? But the second piece to that is long-term measurement of the waves can help us to quantify our numerical models. So we have at CHL and at ERDC, we have a wide range of numerical models, which some of them requires lots of computational resources. Some of them are very fast, but with some limitations. How we quantify these numerical models? We need some observations to validate our models for different types of sources like tsunamis or infragravity waves or sea swells, etc. And then sometimes we need these observations to go and implement new physical processes into the numerical models and later on verify our numerical model with those observations to make sure the model works, right? So this is also for the purpose of benchmarking. And we can compare different numerical models in terms of accuracy with the observations and come up with a conclusion that this model is good for tsunami propagation, for early warning, if the model is fast and accurate enough to issue warning with some level of uncertainties. Some of the models require lots of computational resources, but they are good for inundation modeling. Then we need to understand if these models perform as expected. And all of these buoy observations that you mentioned earlier, they can be used for those quantification. So without those, plus new technologies like satellites or other means of observations, we cannot say which model does better, where, and how we can improve them.
And so the earthquake that sparked this tsunami was a surprise. But other events, and you mentioned some of these earlier, some of these other events such as sea swell, infragravity waves, volcanic eruptions, those can also create dangerous wave events. How do these buoy networks, models, and data analysis all work together to advance our understanding and better prepare our coastal communities?
Okay, so to answer that, as I said, in the Pacific Basin, we have a wide range of different types of waves, and some of them can become devastating, like tsunamis, which are less frequent. And all of these types of observations can help us to improve our numerical model capabilities to go and predict those sea swell events beforehand, and then also provide some advisories for the downstream users. I can tell you some stories of that. So over the last almost 7 or 8 years, we have been the lead developers of unstructured capabilities in a spectral wave model called WaveWatch. And this model is used widely across the whole globe by weather forecast organizations to do wave forecasts. And they use the capabilities that CHL and ERDC implemented in the model to predict sea swell and wind waves. And then also over the course of this work, we also realized how important it is to couple different Earth system models together to improve the accuracy of the models. Because at ERDC and CHL, we are very concerned about the coastal part of the ocean. You also mentioned about the infragravity waves. I think in January 2024, we have a infragravity event in Roy Namur base. It was an army base there, and the base got flooded by that event. So we needed to understand what's happening there. And over the course of years of studying that area, we realized what model is needed to do that. In order to understand if the model is performing well, we need to go and compare them with some real case scenarios where we have observations of these waves by buoy observations, for pressure gauges observations, and different types of new methods like satellite, like coastal imageries, all of these things that I think Kate can comment on them. But I think these are very critical for our development for numerical models and quantification of these models and pick proper tool for proper purpose.
And so I want to talk a minute about the Coastal Data Information Program, or CDIP.
Sure.
It's a collaboration between ERDC and University of California, San Diego. Can you tell us a little bit about that program and our collaboration?
Sure. Yeah. We have a great, really long-standing relationship with the University of California Scripps Institution of Oceanography. I think it dates back to around 1977, so we've been working together for a really long time. As Ali mentioned, there's lots of different waves in our oceans at any given time. And through this collaboration, we've been really focused and interested in those sea swell and the wind-driven waves along our nation's coasts. So we support their Coastal Data Information Program, which among a lot of other different capabilities provides a jointly operated network of over 100 nearshore wave buoys. One of the great things that CDIP does is not only do they maintain and deploy these buoys, but they also standardize all of the measurements coming from these buoys. They make sure that they're high enough accuracy for our coastal engineering applications, and they put them all in one place and make them publicly accessible for all the different end users of this network to be able to use and interact with the data. And I think Ali really highlighted that wave buoys are just such a critical part of our coastal science and engineering toolkit because they provide those observations of waves in our ocean and close to the coast. And from a science and engineering perspective, waves are really the number one input of energy to our coastal regions. And that's particularly important in portions of our coastline with a really narrow continental shelf. So that's the west coast of our United States and a lot of our Pacific Island environments. These observations, as Ali mentioned, really help us understand where our models are performing well, where they're not. And then they can also help us, similar to the tsunami, but for other types of waves, help us identify those hazardous conditions that are occurring in near real time. So our districts really, we use these data for R&D, but our districts also really use these data both in their engineering design of their infrastructure and of their coastal projects, but also in the operations and management of those projects. And I think one of the great things about the CDIP buoy network is because we've been collaborating for so long, we have a really long-standing record. And what that does is it allows us to understand the variety of the wave climate in different locations. And it also allows us to put the current conditions in perspective of prior events. And so when a big storm event happens, not only do we get access to the data in near real time, but we can then, and CDIP does a great job of this in their storm bulletins, is they compare those recent observations to the whole history of data there and can say, hey, this was a really important event. These were the biggest waves we've ever seen here. And that can be really important for the Corps of Engineers' ability to react to that storm event and allow us to really do that data-informed decision-making that helps with the safety of our nation's waterways and our ports.
So, Kate, how has that collaboration and the data that is constantly being collected helped ERDC advance wave and weather modeling and also forecasting?
Sure. ERDC leverages our collaborations with lots of different academic institutions. We work really closely with Scripps, as we just talked about, and other academic universities like Oregon State University. And, the benefit of having all those great collaborations is we get to incorporate cutting edge advancements coming out of academia into our modeling capabilities. We get to work with their graduate students who are really driving the science forward, thinking about the new ideas, coming up with the new algorithms, and doing those detailed tests and assessments of those algorithms. And then we can start to incorporate that into the operational models that our Corps of Engineers districts are using. So in particular, we've been really focused on hazards along the Pacific coast right now. And so a lot of our collaborations with both Scripps and Oregon State is really focusing on improving our ability to model these wave-driven hazards. Ali mentioned that's not only the wind and swell waves, but there's also these things called infragravity waves where we get these water level fluctuations on much longer time periods. And so a lot of our research with both Scripps and OSU right now has been focused on infragravity waves and the importance of them. I think Ali mentioned the flooding that happened in Kwajalein, last year, and that was likely related to some of these infragravity wave-driven hazards. And a lot of those hazards just aren't really well represented right now in the modeling technology that is being used operationally. So that's a really big goal for us, is to get that cutting-edge science infused back into our modeling system so we can make sure that we are making the best engineering decisions that we can.
And over the years, because these tsunamis are happening and they are happening more frequently, we are learning how to incorporate all of this information together. For example, with machine learning to train a model that can digest the USGS information about the earthquake parameterizations and come up with the answer that is it tsunamigenic or not? Is it an earthquake? Does it trigger a volcanic eruption? Does it trigger a landslide? We have the HPC infrastructure at ERDC and across the organization to do very high resolution numerical modeling in a prompt time, and we can provide some estimate of inundation. But before that, because we have developed these numerical models in partnership with academia, all of these numerical models are also handed to forecast organization across the globe, not only inside the US, also abroad or internationally. And they are also using something similar to our numerical models, but most of the time they do not have our capabilities in terms of numerical model and also HPC infrastructures. So we can do high detailed studies to understand the inundation level and also do some analysis on the harbor resonance on all of these things. So these are the most interesting part of these tsunamis, although they can be also be devastating, but at the same time, we learn from them and we can apply them for the future events. As I said, Sumatra cannot happen again, because if it happens and that number of casualty happens, that's a catastrophe. So we need to be prepared. So we need to also improve our modeling capabilities and provide accurate prediction. Otherwise, we lose the trust in the community, and then they do not trust our advisors anymore.
Well, thank you so much for your time, Kate and Ali. I know it's been kind of a wild week this week in the oceanography world. And so I appreciate you taking your time out of your busy day to talk to us. Thank you so much.